Hello students, welcome to my channel. In this video, we are going to discuss about fiber optics. About 2.5 decades ago, most of the electronic communications were carried out with copper cables. You have seen copper cables, right? The signals were electrical signals, and in the recent years, however, we have a new medium called the optical fiber. And in this optical fiber, light signals are used instead of the electrical signals. So it is a new technology, not entirely new. It's a technology where signals are converted from electrical to optical signals. They're transmitted through a fiber and they are reconverted into the electrical signals. So, what is the definition of an optical fiber? It is defined as a cylindrical waveguide made of transparent dielectric like glass or plastic, transparent dielectric which guide lights along its length by total internal reflection. So we'll discuss about this total internal reflection in detail in other slides. So it is the main principle of the optical fiber is based on this total internal reflection. That means when a light, you can see here, when a light enters one end of the fiber, it undergoes a total internal reflection from the walls. And then it proceeds along the length of the fiber and it undergoes successive total internal reflection. Now, this optical fiber is very thin. The diameter of the optical fiber is very thin. It is approximately 7 micrometer. It's like a human hair. It's very thin like the human hair. Now remember one thing, that a thin strand of metal is called a wire and a thin strand of dielectric material is called the fiber. Now optical fibers, as I've mentioned, they are cylindrical in shape. In general, they can be divided into three coaxial regions. The first is the core, second is the cladding, and the third one is the buffer. So what is core? Core is the innermost cylindrical region, which is basically the light guiding region. So this region is the main region which guides the light through it. And next is the cladding. What is cladding? This core is surrounded by this cladding. This is the coaxial middle region. The one thing you need to remember, that the refractive index of the cladding is always less than that of the core. That means if the refractive index of cladding is N2 and refractive index of core is N1, then N2 is always less than N1. Outermost layer is the protective plastic jacket called the shield or the buffering core. It's a buffer. So this encloses the core and the cladding, and it basically protects the core and the cladding from the abrasion, contamination, harmful influence of the moisture, and it also provides mechanical strength. It increases the mechanical strength of the fiber. Now here I have shown that how small is this core, cladding, and this buffer region. You can see here the diameter of the core is from 7 micrometer to 63 micrometer. So it's the smallest part. And then we have the cladding. The diameter is around 125 micrometer. And the buffer or the protective sheet, it ranges from 250 micrometer to 900 micrometer. So this is the structure of the optical fiber. So optical fiber consists of a core, a cladding, and buffer region. Now we can summarize that core is the inner light. This core is the inner light carrying region. Cladding, cladding is the middle layer which serves to confine the light to the core. And lastly, the buffer, it encloses the core and the cladding, which protects the fiber from physical damage and environment effects. So this is all about the structure of the optical fiber. Now the transmission optical fiber is based on the principle of total internal reflection. Okay. So let us first recapitulate what is, I'm sure that you all know about total internal reflection, but still let us recapitulate what is total internal reflection. Now you see here the total internal reflection when suppose, so first let us define the medium. So when the refractive index of a medium is very high, we call it as a denser medium. When the refractive index of the medium is low, we call it as a rarer medium. Okay. So let us take the refractive index of the denser medium as mu1 and the refractive index of the rarer medium as mu2. Now a light is traveling from the denser medium to rarer medium. Now as we know that when a ray of light passes from a denser to a rarer medium, it always bends away from the normal. Okay, so here this, if we apply the Snell's law, so from Snell's law we get that mu1 sine theta 1 equal to mu2 sine theta 2. That means sine theta 2 equal to mu1 by mu2 into sine theta 1. Now when the angle of incidence, so this is theta 1, let us take this theta 1 as the angle of incidence and theta 2 as the angle of refraction. So this is the refracted ray, this is the incident ray. So theta 1 is the angle of incidence and theta 2 is the angle of refraction. Now when the angle of incidence theta 1 in the denser medium is increased, this theta 2 also increases, right? And this refracted ray bends more and more away from the normal. So if we go on increasing theta 1, so this theta 2 will also increase and it will bend more away from this normal. So what happened at some particular angle theta c? Now you see, let this as picture A. So if you see picture B, now at some point, some angle when theta 1 is equal to theta c, the refracted ray grazes the boundary between the denser medium and the rarer medium, so that the angle theta 2 is 90 degree. So what happens if we further increase the angle, that is, if the incident ray is incident at an angle greater than theta c, it will be totally reflected back into the denser medium. So this is known as total internal reflection. So the phenomena in which the light is totally reflected the denser from the denser to rarer medium boundary is known as the total internal reflection. So you see here when theta 1 is less than theta c, when theta 1 is less than theta c, here you can relate to the picture A, the ray refracts into the rarer medium. When theta 1 is equal to theta c, the ray just grazes, you see here, the ray just grazes the interface of the rarer to denser medium. And when theta 1 is greater than theta c, you can see here the ray is reflected back into the denser medium. So this phenomena is known as total internal reflection. Now if we calculate this theta c is known as the critical angle. At this critical angle, the refracted ray faces the rarer medium and denser medium boundary. Okay, so this is theta c, this angle theta c. So when theta 1 is equal to theta c, we see that theta 2 is 90 degree. Okay, so from the Snell's law we get mu1 sine theta c is equal to mu2 sine 90 degree. 90 degree is 1, so mu1 sine theta c is equal to mu2. Therefore, sine theta c is equal to mu2 by mu1. Okay, so mu2 is the, as I have mentioned, it is the refractive index of the rarer medium, and mu1 is the refractive index of the denser medium. So when the rarer medium is air, that means if this is air, so mu2 will be 1, so mu1 will be mu, and let us take mu1 as mu, so we get sine theta c is equal to 1 by mu. So theta c is the critical angle, and we get sine theta c is equal to 1 by mu.